Okay, people. Good evening. I think it could probably be a bit louder. Oh my goodness, volume control. Okay, I think that's probably a bit better. The assignment is due at the end of the week. Do I need to talk about the style guide? I'm just a little bit concerned that maybe people are not aware, I suppose is the right word, of what the style is. There's one thing, things like multiple return statements are not a problem if used wisely. Switch statement is perfectly okay. Continue statement is not recommended, and you need to have good program to justify it. Used sparsely is not a problem because they're usually very clear what they do. They're usually a sign of very lazy programming. There are exceptions. So in the hands of a competent programmer, a continue statement is not a problem. One thing is an absolute strict rule. Externs, globals and statics are not allowed. Do not use globals, externs or static. They destroy structure. I have used them many times in my past and used very carefully, very complex system. They can be very effective, and when systems are very complex, sometimes they're really necessary. But in this course, in the small programs that you're writing, they are completely unjustified. So I will come down very hard on anyone who uses a global in particular, and statics as well. They're just not needed. There's no way you could argue your program needs it. Okay, the assignment is due. I have a consultation on Thursday this week as well for those that couldn't make this afternoon. And don't forget to register your exam preference. I have to write the final exam this week and, of course, the mid-session this week. So I'm putting exams together at the moment, which is really difficult, not having done the second half of the course and not knowing exactly how far we're going to get. Okay, I think we can go straight on to the lectures. There's no serious changes to the lecture last week. This week I want to get on to LinkedLists. Does it accept me? Yes, it does. Excellent. Now, I don't think this will take 2 hours. I think this will be quite simple. I want to actually... I do it a bit unusually. I had a quick look at the website, the Learn C website, to see what they did. And there's not a problem. And I've had a look at Sedgwick, and it can get very messy. And if you're not comfortable with pointers, your head will hurt, in a sense. You will get very confused. So I'm going to try to take it a little bit slower, this lecture, so there aren't that many slides, but there's a lot of program. The trouble with linked lists is there's a lot of housekeeping. You've got to keep the links intact. You've always got to make sure you've got a head, you've got a tail, and all the links are correct. There can be no mistakes, otherwise it all falls down. Extremely fragile. A linked list is extremely fragile. They're hard to get right in the sense that when you program, they're very easy to make small mistakes and to spend a great deal of time in debugging. Now, okay, so care is needed and understanding pointers. They're actually used quite a lot in operating systems. They're very efficient in terms of memory usage. The problem with arrays is, in some sense, they're a lie. They're a lie in the sense that people want large arrays. And when you ask for 1 million or 10 million integer array, the system will say fine, but when you actually do the allocation, or when it actually does the allocation, it can have a lot of trouble finding room for you, and it has to fragment and squash and do all sorts of things. So behind the scenes, there can be a lot of work to get you a contiguous piece of memory. An array must be contiguous. So it has to do all sorts of gymnastics to get you your memory. Linked lists are extremely agile. They let you can create them and allocate them in small increments very easily. You can delete from a linked list very easily. So you can reduce the size, you can increase the size, they're very volatile, they're very easy on an operating system. They're harder on the user because they do require more housekeeping. You have to, again, when you remove links, remove nodes, you must keep the pointers or links intact. So that, you'll see, is the big problem. So they have quite a lot of disadvantages. They cannot do random access. Of course, you just can't go to the middle. You must start at the first node and work through, well, in general, or to the end node, come back in doubly linked lists. So you do need to start at one of the ends. You can't go into the middle. That's a major handicap. You can only do sequential access. And really, if you compare that with arrays, well, arrays can do sequential access a lot quicker than a linked list. An array, you just have this index, which is an offset. You don't even need an array. You just have memory and you offset it. And the addressing modes let the computer fly through the array. So in terms of speed, a linked list is really a very cumbersome data structure, because every list has an address, and that address has to be looked up, so it has to go to another part of memory, and that's a slow operation. Large overhead, mallocing for every push operation, so if you're changing the list a lot, you've got an expensive operation, and of course there's a pointer for every element or every node in the list. If performance is an issue, you'll see a little bit later on in the course that binary search trees are far superior in most applications and are almost always better. Not exactly always. So binary search trees are a more sophisticated form of linked list, you could say. So really, you could argue that even in operating systems where they use linked lists, binary search trees would be a better solution. But, okay. A linked list consists of nodes, and in particular a special node which tells you what the first node is, or the head. In a sense, that is the big problem. It's a bit, sometimes I think about it, I compare it with a malloc. When you do a malloc, you get a pointer to memory. Now that pointer to memory, you must not lose. We saw that last week with our elephant, that you must keep that first pointer intact or be able to get to it, because if you lose it, you've got a memory leak. And malloc, where you've lost the value of the address, the first address. Same with a linked list, you cannot lose that first pointer, the first element, the pointer to the head of the linked list. So you have nodes, you have a special node as the first node, and another special node that acts as the last, which is usually just null. It could also be a dummy node, and it may also be the first node because it could be circular. A node is a structure that contains data and a pointer to the next node. It's as simple as that. It really summarizes a linked list. It is a series of nodes where each node contains data and a link to another node. In that sense, it's totally recursive. There are many ways to define a linked list. And if I gave you one now, you'd probably say, okay, I can sort of remember that a bit, but I'm going to give you 3 slightly different ways, which will probably confuse you, but okay, you'll see now, okay, I better choose, otherwise if I try to remember all 3, it'll just go crazy. Typically, I think they overcomplicate it. In the literature you often find there's a data structure for the nodes in the linked list, and there's a special data structure for the first node. It's that important. And that's quite a lot of overhead, because if you look at the typically first declare a struct and then declare a struct, another struct containing a pointer to the first node, you see there are two type defs here and two struct definitions here. And that's quite a lot of overhead. I won't even go into it because there's no point if you're not going to do that. Sedgwick has a much simpler approach. It's simply a link to a struct. But what I'll use it is a slight variation of that, is simply one type def with a struct node and a struct node pointer in the struct node. Okay, it's one type def. Struct node appears twice. It's, I think, the smallest, simplest way of representing a linked list. I tend to keep things as simple as possible. The less characters, the less possibility of mistakes. Now, unusually what I've done now is I give you a silly, maybe I should change that, silly useless example that shows you the very basic functionality, getting rid of really the first problem and traversal problems and linkages and all this complicated stuff, which you can get really messy with previous as well in general. So what this little example does is it just defines a linked list of two nodes. No libraries are required. It creates simply, the linked list is created simply by a malloc of two nodes, two different mallocs, reading and inserting the data and linking them together. With two nodes, you need one link. So you do a malloc, read the data into that malloc. A malloc, read data into that malloc, and link the two together and null terminate that one. Simple as that. And that's a linked list of two nodes. So I call it LL2I, linked list two integers. And you see the little definition of there, struct node twice, type def, linked L is what I call it. And that's what I always use. And we define there, yuckus. Now I'm going to change that. I changed the names to make them, I thought L is a terrible name because it is looks like one. I didn't, so I've changed it by hand, so if I don't do it now, I'll forget. Okay, I hope that's right. Fortunately, I can't compile it in situ here. So, N1 and N2 are both linked list nodes. They have type linked list, and that is just a node. The fact that it points to something else is irrelevant until you fill it in. So we have two nodes, N1 and N2, and I do a malloc on both. I do two mallocs, and I make sure they're both non-null. And if they're non-null, then I ask for some data from the user. I scan the data, and if that's there, equal to 1, I set the data in the first node, N1, to that data. Then I read the second, I ask the user for a second integer, and if I get that second integer equals 1, then I set the second node's data to that number, the number that's read. So I've got N1 data and N2 data here. I'm sorry, I was a bit too fast. So I've read the two numbers in the scanfs. The only other thing I need to do, or two other things I need to do, is I need to have the link in both nodes filled in. The first link will be a link to the second node. So I have N2, so the first node link will be N2. N1 next is N2, the link to the next node. And N2, of course, doesn't have a next because it's the last node, there are just two, so it has null. So we see here N1 data, N1 next, N2 data, N2 next, all filled in. So all the data has been filled in. Just to do something which is a little bit more generic, I'll show you here the traversal. traversal of potentially an arbitrary long linked list. Could be 100, could be 1,000, could be 1,000,000, could be 1,000,000,000. You start at the first element, in this case n1, and I keep going until I get a null, where each time I increment the pointer to the next node. So you can see the pointer starts at a node, basically, and does something with the data, then takes the next of that node to go to the next pointer. Another iteration, and every time it iterates by taking the next of the node that it's currently working with. And that's how we walk through, traverse the linked list. And here all I'm doing is printing the data. So here you see the two mallocs for the two nodes. You need a malloc for every node, and the 4 assignment statements, basically. 2 scans to put in the data, 1 link connector between the two, and a null terminator on the second one. Now that's about as simple as you can do it. You must have 2 links. You do need at least 2 nodes. You must have a link between the two, and you need a terminator. And because we've only got 2, we know what the first one is. It's N1. So we don't have to sort of remember that. We've just got 2. Basically, there are sort of 2 variables, if you like, N1 and N2. So we don't have any problems with naming. Very importantly, I tidy up. I free both N1 and N2 after I've printed the values, and I untangle them by setting N1 and N2 to be null after they're freed. So if I do extend the program, I can't have a pointer problem. I can't try and access the pointer that's been allocated. Oh, I didn't run the program. I thought I would have had an execution here, but I don't. Okay. That works simply, and it's trivial. Having seen, what data is and what a pointer is, or what a link is in a data node, I complicate it now and go to the next level, and I have the string Woolloomooloo. I can't even remember why years ago I chose Woolloomooloo, but it's the string I decided on. So I want to extend the 2-node program. Again, no library required, and again, it's just a single program. No ADTs involved, keeping it just a simple program to show you how you construct a linked list and how you traverse a linked list. What you free and how you can delete. Do I show you how you delete? Possibly not. We'll get to that. So here I have my struct. I've done it slightly differently here, which you just only noticed this morning. I actually define just my struct node. This time I call it LLL, which has data, and it has a link to another struct, the recursive link. I type in, I don't have any type defs this time, I've left the type def out. So I type def the struct LLL to letter, and I use letter now as my type. I have 3 variables in this program, L, first letter, first L, and previous L. And now this previous is a beast. You'll see whenever you do any linked list programming, having to know previous is a real pain. And if you don't know what previous is, then you can't do things like delete a node. Delete a node requires you to know what the previous. So every time you walk through, you have to know 2 things. Who I am and what was before me, what was previous to where I am at the moment. You'll see in a moment why. It comes to the very real essence of the problem with linked lists, but once you understand it, you sort of understand everything there is to know. So this little program has an inbuilt string, Woolloomooloo, and that's referred to by W. So it's a character string W equals Woolloomooloo. And what this program does, it assigns each of the letters in Woolloomooloo to a linked list. Each letter goes into a node in a linked list. So I don't know how many letters there are in Woolloomooloo, but the linked list is that long. One node for each letter. For each letter, hence, I've now got to create a node, W for the O, for the O, for the L, for the L, etc. So I've got to create a node, and I've got to fix the links up. I create the node by doing a malloc, just as in the two-node linked list. So the first thing I do is a malloc, and I assign that to my L. Well, remember L is a letter. That's my type def. And that's the size of letter here. So I've got a malloc of size of letter assigned to L. Well, L is a pointer to letter. Really important. That's the basis here of a node, a letter node. The letter node again is the letter itself and a pointer to another node. And every node has a letter and a pointer. As long as it's not null, if it's null I get out. Otherwise, really simply, I give the letter in that node its value, which is the letter I just read, and I null the link for safety's sake. You don't want to leave it undefined. As it turns out, that null gets overwritten in all of the nodes except the very last one. The very last node is when that null doesn't change. You'll see that in a moment. I think this is a really good example to understand really what a linked list is doing. So here we see the star W. The W, remember, was the start, if you like, starting address of Woolloomooloo. Star W was the actual W, or the O, or whatever, because it gets incremented further down. Oh, sorry, it gets incremented through the for loop, where you see on the right-hand side here, W++. So the first time through, W equals, maybe it's a terrible name actually, W is W. W is the name and it points to W. Second iteration, the W points to O, then points to O again, then points to L, etc. Okay, so the W is just reading through a character sequence. Each of those characters are put into a node. In this case, you see the letter field in that node is being assigned by star W, and the indicate or the pointer is set to null. Now, the next if statement is weird for you probably, and there are many ways of doing it, tricky ways and ways that have advantages and disadvantages. This is the way I do it. I like doing it. I don't know why. In one traversal, from beginning, the first node to the very end, I go through and I inspect every node. Now, if I'm on the first node, that's important. I must remember that node, because that's the first letter of the word. That node will be when W is the same as Woolly, the actual data. So when W is Woolly, the same address, I'm starting. And I've got to remember that node. And that's why that node becomes first L. And that's the only time I touch first L. So that if statement is done, I must count, 3, 6, 9, 10, 11, 12, 13 letters. 13 times I loop through, go through that for loop. The very first time, W and Woolly are the same address, and therefore first is set. Every other time, of course, that's not true. W and Woolly are not the same. In that case, we do the else. And in that case, because we're not at the first node, we're at the second or third or fourth or fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th or 13th node, we have a previous node. We only have a previous node when we're not at the first. When we are at the first, we want to know which node we're at, and we remember that. But after that, we've got a job to do. The job we have to do is we have to backpatch the previous node to put in the link. Because you cannot know what the link is to the following node until that node is read. If you read W, you have a link to fill in. How can you fill that in till you have the node that's been, or the malloc has been done to tell you where the O is going to sit in memory? You don't know until you read the O, do the memory allocation, you've got the memory, then you say, okay, I've now got the O, I can go back to the W and fill in where I am, the address. That is the link. When you read the second O, you can backpatch the first O's link. When you read the first L, you can backpatch the second O. So in this if-then-else statement, you're doing a lot of housekeeping. The first time again, through the loop, you remember, basically I always think of, it's sort of the identification, you remember who you are. First is remembered, you know from then on, first is the start of the linked list. From then on, the if-then-else statement is used as backpatcher to put in the links of the previous one. Now there's one link that doesn't require backpatching, and that is the last link, the last node. One link, sorry, well, I said that wrong. The last node doesn't require backpatching. The last node, because its link is to who? To null. That's the null that I initialized every single node with. So every null, remember what we started with? Line 23 and 24, every single on line 24, next was put at null. So whenever we get, so all of the nodes come in, set to null, and they're overwritten when we backpatch on the next iteration. Set to null, read a character, backpatch, overwrite the null with the address of the malloc. Next character, read it, do a malloc, read it in, that's the address, overwrite the null of the previous character. Okay, you see we step to the right, you read in there, do the malloc, read in the character, create the node, backpatch. Read another character, put it in the node, we have our malloc, we have our backpatch, the whole way through till you get to the last node, and it never gets backpatched. It backpatches the second last node, of course, but then we stop. So that null in that last node is not touched, it's left alone. So we now have a situation where we have the first node is referred to by first L, and the last node has a null link in it, the only one. Every other node is being backpatched. Okay, and that's our linked list. It's simple, it's clean, and there are other ways of doing it. I like this the most, for no particular reason. That's 90% of the work. The other 10%, it's important 10%, is this backpatching can only work if we know what the previous node was. And that's what we do rely on, because I said, well, okay, I do in line 30, previous L next is up, I do the backpatching. How do I get back there? There's no way of going back in a normal single linked list. If I didn't have this previous here, take this line out here where I remembered the current node, okay, I've got to call that now previous because I'm going to increment it. I'm going to step. And when I step, I lose the previous one. So I better remember the previous one, because when I backpatch in line 30, I need him. Okay, so this is preparation for the next. So every time through, you have to backpatch the previous one, which you can do only because the previous time you remembered who you were, or who you are, or who you're going to be called. previous. Okay, so there are things that's really interesting, sort of fun in a way, when you sort of get your head around, oh yeah, sure, and when I go through, I've got to call myself previous, so next time through, because L will be overwritten, of course, when you actually step through. L keeps on going. So, and if you think about it, goodness, yeah, I can't go back unless I have a doubly linked list. But if you have a doubly linked list, then you have to have 2 pointers. One going backwards, one going forward. You've got 2 pointers to keep up to date. You've sort of got to keep forward and backwards, everything square, and okay, make sure it all links properly. Then you've got to need to want to do it, because mostly linked lists tend to have to work in a particular direction, alphabetical direction or some chronological thing. There'll be some reason for the ordering. And there aren't that many applications where you actually need to go 2 directions. And you need to have a pretty good reason to want to increase the storage by yet another pointer. A pointer is 8 bytes. So number of elements times 8, that's a big overhead. So 1 pointer is bad enough, you need 2, you've got to have a good reason. So I tend to think of it that way. Singly linked lists do an awful lot, and doubly linked lists are for a small number of applications on top of that. It's a very instructive little program which gives you the feel for what's actually involved. And it's still, there are no libraries involved, there's no ADTs involved, it's what you see is what you need to do. It is exactly the minimum amount of work. Must remember the first node. You must backpatch. You cannot do it without backpatching, because you cannot know where to put the link to something if you haven't read that something. Because it always, if you think about it, a linked list links to the following. Well, how can you link to the following if you haven't got it yet? So you have to read the following, and then you go back and you patch. We call patching, you put the correct address in the previous entry. Okay? But that's the problem in a sense, and that's why I come back to the previous. How can you go back to patch the previous if you haven't remembered it? So for example, if for some reason you need to do, and it's not, well, it's actually make a good question. Say you wanted a linked list, there are 2 pointers every node, and you point to the following node and you point to the second following node. That would be quite a little interesting exercise. I've never seen it anywhere. If you think about it, what does that mean? You do exactly the same algorithm, of course, or loop, but you'd have to have 2 previouses. Remember a node, you have to remember the previous node, and the previous one again, the double previous, if you like. So when you do the malloc, you put the data into that node, then you can backpatch the previous one, and you have to backpack the previous one to that one too, backpatch that one too. You could do a double backpatch. And there may be some application where you need 2 generations ahead. So when you have a node, you can find the next 2 generations really quickly. The addresses are in that data node, with the data in that node. Okay, so this is the absolute essential kernel of what linked lists are all about. You understand that, really there's nothing else to linked lists. There's simple little mallocs which require little pieces of memory to be linked together. Here I show you that traversal, very similar to the N1, N2, the 2 node, where you start at the start, you see first L, I need first L, don't touch first L. And I go to the end, remember the next node of the last node is set to null, that's my terminator, and I step through L equals L next. It's very clean. You'll see that hundreds of times when you do a lot of linked list programming. That's the standard for loop. You should almost be able to write it without thinking. Start at the first, go to null, increment, L equals L next, or whatever the next link is. And each time, all I'm doing is printing the letter, the data field in that node. So the links are only there to get through the data. Okay, so that's a neat traversal. Freeing up, I've done all these mallocs, of course got to free it up. So here, in this while loop, first thing I do is I print F, cleaning up, freeing, then temp is my next. I then print the letter and free the node. Why don't I use a for loop? Why did I change? What am I doing? In the line 37, 38, that for loop traversed from the start to the end. In line 44 to 49, I traverse from the start to the end. From the start to the end, from the start to the end. For loop, while loop. Why the difference? Why not two for loops? Well, the content looks a bit weird. Why?
Once you free L, L will be null. Once you free L, L will be null.
Yes, can you expand that a bit more? What do you mean by that? It's a bit too cryptic.
Because if you free, once you free the first node, and the L will be none.
That's exactly. That's right. It's a question of ordering, if you like, ordering of operation. If I immediately just did like I did in 37, 38 and said for first L until null, L is null next, free L, okay, very simple, free L instead of the print. The first time it does L next, I've just freed the node. How can I do the next? L next, the very right-hand side of line 37, the increment, if you like, the next step. I can't do the step because I've just freed the node. I can't use it. It's gone. Okay, so I'm destroying myself, and then I have to use myself to get to the next node because the link is in me. The link is next. So if I destroy myself, I've got no link anymore. Gone. Link's gone. So I have to first remember the link. I put it in temp. I didn't want the data. I could have done the data first. I could have done the printf first, if you like. That's no difference. I could have done basically any time before the free. I need the next and I need the letter. Then I can free. And here I then say, well, okay, now, because it's a while, because I didn't need to step through until null, so because I haven't got a for loop, I then have to reset the temp, the L to be temp, which is the next. So I've got to do it by hand. So I need if you like, a temporary location, temp, to store the next so that I can zap the node and then go to next. I go to next by line 48 and go through the while again. And eventually, the next will be null. And when the next is null, that line just copies null into L and it will terminate the while loop. Now, there are other ways of doing it, tricky ways with if statements and all sorts of things, and you can use for loops if you use them in a tricky way. But it's just I've just accepted this long ago that this is the best way of freeing a linked list, a simple while loop with a temporary location. And that's the kind of mindset you need to take, that a lot of linked list stuff is very repetitive. You free up linked lists always in the same way. You don't even try to muck around with different ways of doing it with for loops and if statements to remember and all sorts of weird things. You can, and of course you could translate that while loop into a for loop. I just have a pattern, do it the same way so it doesn't go wrong, so that you don't confuse yourself. If you do decide to do it in a for loop, and you could of course restore or put something else on the right hand side there if you wanted to, but it'd be more complicated. Okay, so there's a simple example, and I do that one here where I show you the link structure has stored and the 13 characters, Woolloomooloo, and in cleaning up, freeing WL, etc., cleaning them all up, bringing out each letter as I clean them up. Okay, now, standard, they are two simple little examples. No ADTs, no libraries of anything, nothing's called, nothing's standard. They're very specific to a specific problem. In general, you tend to see linked list functionality in very generic terms. How you delete a node from a linked list, how you insert a node of a linked list, how you change the head, how you add to the tail, how you reverse a linked list, all this sort of very generic operations that you can perform on a linked list. So, for example, put the print traversal above in a function. If you want to print a linked list, in general, here's the for loop, which I showed you earlier on with the Woolloomooloo. You have here a for loop starting at the head, traditional name for the start of a linked list, going onto the null, traditional terminator. You increment the loop index, which is a pointer, to the next, and you print the result. So that's a slightly more generic form of that previous printf, where it's become a function. Function taking just the head, the first letter in Woolloomooloo, or just the head in a generic case. So if you call this print list function with first L, in the case of Woolloomooloo, it would do exactly the same thing. The second example, freeing a list, you see I put the while loop inside a function. So you can put the operations of freeing or printing inside functions. Now you can also put the allocation, the create a node in a linked list inside a function. Just like I did in the two node case, just like I did in Woolloomooloo, I create a node, I put the data in, the data V comes as in the argument list, and the next is set to null. It's playing it safe. You don't leave it open, saying, oh, I'm going to backpatch it anyhow, I don't need to fill it in. That is very dangerous indeed. So play it safe and make it null, and assume that you will come back sometime to fix it up to keep the list intact. And you return the allocated pointer, of course. And deletion, now deletion is where it starts to get even more fun. I usually write a deletion operation by first, it does, if you delete the head of a list, oh my goodness, you're going to seriously change things. Be very careful you don't delete the head of a list, because you could lose the whole lot. If your list is 1,000,000 characters long, 1,000,000 nodes long, you delete the head, you've lost the lot. You've got to be very careful what you're deleting. So the first thing I do to check whether I have got a list at all, is it null? Get rid of that situation. I think actually in this particular case that it will work without even making that check, but I like to be very safe, and if it's null, I've got nothing to do and I return the null. Now, I set a pointer to my head and I check and I go through. While current is not the node that I want to remove, I'm removing a node, a whole node. That node has type linked list, line 1. I've got a linked list as the first parameter and a linked list node a second parameter. The fact that one's a list and the other one's a node you can't see, because they're both just nodes which have pointers, and one has a pointer to something and the other one has a pointer to a whole list behind it. Okay, so now I go through that list. I start at the first node of the list, head, that's the first parameter, and I keep going until hopefully at some point I reach null. I will reach null, not hopefully, I will reach null if the node is not in the list. If that's the case, then my current comes out of that loop, loop 11 to 14, with the value of REMN. It's the value, current is the value, has the value REMN. If that's not the case, there is no remove node that I can remove, it's just not there, then of course current will end up being null. If current is not null, then I found him. I found the node I want to remove. What I have to do then is, if current is not null, if previous is null, then the current will be head. Now I have to look very carefully at what I found. I found the node I want to remove. Okay, which node is it? Is it the head? Because if it's the head, I have a problem. Sort of a problem. I've got to be very careful. If it's not the head, I can do something. More standard, if you like. If it's just a node from second or third or fourth or anywhere else, except the head, I can do something. I've got a previous node that I must use. So I have to backpatch that node to remove myself out of the linked list. This is where it gets hard. This is where you've really got to think back to Woolloomooloo of why I had to backpatch to build the list. There I was backpatching. Here, I'm using the concept of backpatching to remove myself, to eliminate myself from the list, which is what this is about. It's actually removing, deleting an element. In this case, it's called REMN, remove N. So, if I'm the first node, if current is REMN, and that is the head of the list, then there is no previous, and in that case, the head will now have to be, I'm removing myself, I found myself, I'm the head of the list. To remove myself means that the new head is the next node. So if I was the head, if I am the head, and I'm being removed, well, the new head is the next node to head. So current next is the new head. It could be REMN next. REMN next is also true, because at that point current and REMN are the same thing and they're both the head. If I'm not the first node and I'm removing myself, then I've got to backpatch the previous node to skip me. You skip me by setting the previous node's next to my next. So obvious, but you do need to think. There's my left neighbour, there's my right neighbour. My left neighbour has a link to me. I have a link to my right neighbour. Two links, to me and away from me. If I'm removing myself, my left neighbour's link has got to be to my right neighbour. So my left neighbour's link has got to be my link. So my left neighbour is previous, his or her next has got to be my next. So simple, but you do need to look at it and think about it a bit. It's really, really important. That's used by every node that you wish to remove, but except for the first node. The first node, again, there is no previous, so if you try to do that, and you're removing the head node, you'll get segfault. Now, that's it basically, because all I have to do then is when I've removed myself by telling my neighbour, left neighbour, to go to my right neighbour, to put them through to each other, then I'm redundant, I'm useless. I don't exist in a sense, but I have to free the memory allocation that's been made in the first place, sometime in the distant past. So I have to do a free, and I even do a nullify here of the pointer so it doesn't dangle. Because I don't know what node I'm removing, I must return the head, because the head may be the old head in case I was removing something somewhere in the list, or it may be a new head if what I removed was the first node, the head. So if I remove the old head, then the new head's going to be its next. That was what we did in line 617. Head equals current next, so there's a new head. So it's possible there's a new head, so I must return the head that comes out. Okay, so there's deletion. But you can see there's a bit of backpatching going on there. I've got to look at the first node. You can see the elements that are presented with Woolloomooloo. You understand that if statement in that Woolloomooloo, what backpatching, it's all there, but it's in a different form here, because there I was building and backpatching to get the links correct all the way down the line to the last O in Woolloomooloo. This time I have to backpatch to get rid of myself. I'm doing it in the other way around, in a sense. I'm destroying, or I'm taking something out of the linked list, and I need to backpatch too. You must get comfortable with backpatching. It's part of linked list development. And that's about it, I think.
Why only cur is free?
What was that?
Why only cur is free?
Because you've only deleted one node. You delete one node, REMN. And REMN is the node you're looking for. And you've got this as long as there's room, and one node somewhere has the same, is REMN. It's the node. It's an actual physical node which has the same data as what you want. Okay, you're removing a physical node. You're not removing a value. It could be any number with a certain value. You're removing a physical node. And the physical node will only appear once. So you remove that. You go through until you find him. And when you've got him, you take him out. There's one thing I just realised that I didn't cover, and if you remember with Woolloomooloo, we needed to remember the previous node to do the backpatching. So the last thing we did in the loop was we set the current to the previous, so that when we looped around and we took on the new link, which is the next node, we lose the L, of course, but we've saved it in previous. So we have always the location of the previous node. So previous is used in line 20. Where did that come from? And I just forgot to say this. You've got to... Where's previous come from? It's not hard to see. Previous, where was that set? Well, in line 12. You see what line 12 does? When it goes through looking for REMN, going round and round and round in circles, each time taking a next, looking for REM. Where is REM? Where is REM? Where is REM? I found REM. When it finds REM, what it does every time it goes through that loop, it remembers the previous. So coming out of that loop in 11 to 13, 11 to 14, I don't only know current, I also know previous. I actually know two things. And I need both. You always must have two nodes to delete. Same idea with Woolloomooloo and backpatching. When you delete yourself, you know who your right neighbour is, but you also have to know who your left neighbour is. Well, that's me, of course, and you're over there turning it around. So you have to know both sides. So working left to right, in my case, I have to know the previous person so that I can backpatch them to my right neighbour to get rid of me. And my left neighbour I can only know, there's only one way if I don't have a doubly linked list, only know it if in my traversal to me, I remember the previous. So you sort of piggyback that while loop and you say, well, I don't only want to know when I found my current, REMN, I also want to know the node beforehand. So that prev from line 12 falls down basically and ends up at line 20 to do the removal. So you can see there's some thinking. You can think, my goodness, I love arrays all of a sudden. I think now arrays are wonderful because none of the stuff is necessary for an array. You really have to do the housekeeping by yourself. in the case of linked lists. And I actually tried to draw it here. Delete from the middle or delete the end node is all the same. When I remove B, B's left neighbour has to be given the value of current next. So previous next equals current next. That's the most important line in a sense. That's the thing that does the removal. That is the characteristic, if you like, or the actual real operation that does the removal. Everything else is sort of getting to that point where you know who you are, who your left neighbour is, so that you can use your pointer to your right neighbour to give to your left neighbour. And say, good luck, left neighbour, I'm off. Okay, you hand it over to your left neighbour to converse with, or to talk with, or to do something with your right neighbour. And if you're deleting the head, well, that's a simple case in a sense, but it's a tricky case. You've got to make sure you give it a new head. So if the character, so the node that you want to delete is A, then B, which is A's right link, that's got to be the new head. So you see the current, if current is head, then the new head becomes the current's right neighbour next. That's everything what I've just said is in picture form. So they're the two cases that you have to separate in the loop to do the deletion. Now, as if that's not enough, now we start to get and bring the ADT on top of that and make it an actual concrete data structure implementing an abstract data structure. So instead of last week where I used a rather boring, rather bulky array, remember I had a type def, had a struct, which had an array of size height. That was the implementation, the concrete data type that I was implementing my stack with, or quack with. Now I'm going to implement my quack with a linked list, not an array. So I get a second ADT. As ADTs are, of course it's an ADT, the interface I showed you before is exactly the same, except this time you'll see your favourite cush operation, 9, So I've got a cush and a push. Push goes to the top, or cush puts it on the top, and the cush puts it at the bottom. For the rest, there's just standard pop, is empty, make empty, and show quack. And the struct is just a pointer. We don't know what it is. We have seen last week that it can be an array, and this week we see that it in fact can be a linked list. And you can't tell in the client which one it is. Well, in a sense, you can now a little bit because I've had to give them a different name. So when you compile it in, you've got to choose between the two implementations. We implemented this ADT using an array last week with a maximum capacity. Of course, I could have taken that maximum capacity out and used mallocs and increased the size of the memory if I needed more. And that's not untypical. There are many applications where they allocate a certain amount of room, and if you need more, they say, oh, you need more room for your stack. You've reached the top of the stack, you've overloaded the stack, then they just double the amount of allocation and they just go on from where you left off. So that's quite typical. Now, with a linked list, you don't have to do that. A linked list, you've got a quack, which is based on the linked list. That means you can just keep on adding, in a sense, forever. As long as you've got a memory address space, there's no limit to the size of the linked list. Each element in the quack is now a node in your linked list. As the elements are pushed onto the quack, the list grows. The length is unbounded. As an ADT, it's unbounded. Of course, there will eventually be address limitations. Push cannot cause overflow, so overflow does not exist with a linked list. Your malloc can fail out of memory, but it doesn't overflow. You can't overflow a linked list, in theory, unless you've got some weird application where you want to set some limit to it, of course. But natural linked list, it has no limit. You can underflow, of course. You can try to take something off a linked list, delete something on a list that's already empty, and insist that you want to remove something, but it can't be because there's nothing there. So that is a case of underflow. So you're popping something from an empty list. So I call that now quack LL, and it's not simple. It takes Woolloomooloo, if you like, as a starting point. You can see it as a mindset or way of thinking about building a list and backpatching and remembering the first node. They're the really fundamental things. You sort with remove node, delete node, but again you had to backpatch. So when you're creating and when you're removing, you've got to be very careful to backpatch to know who your previous or your left neighbour is. Now, so the reason we need to know this is because when you push, you're adding to the linked list, to the end, to the top, but when you pop, you take off. So you are deleting a node, hence that delete operation which you just saw. Now, because we have push and we have push, you could be affecting either end of the linked list as well, which means you may have to go to one end to put something, or you may have to put something on the other end, the starting end, which means that you have to create a new node and give the new head the old head as next. You should start to be thinking a little bit like the node data next. If I put a new head in, what's that going to mean? Well, I've got the old head, that's going to become my second node, so I just have to connect my new head's second or next node to my old head, and more or less that's okay. And if I'm going to put it at the other end, then I've got to walk all the way through the list. If it's 10 billion long, well, I've got a long walk. And when I got to the null, finally got the null, you put a link into your new node, the one you've created, the one you want to insert, assuming you're doing a push, and then you put a null, of course, in the new node that you've added. So, here we define our linked list little structure. It's just as simple as before. It's a struct data and next node. And I create my quack, and this is where there's a little, you could call it a wrinkle, a little complication which you have to get your head around a bit. And that complication is there's a special starting node which we just simply call the head. And the head is there, it's a place, if you like, it's reserving, it's the first L in Woolloomooloo. It's something that always exists, even if the list, the linked list, or the queue, the quack, or the stack, whatever you want to call it. It's a linked list, that's the concrete data type. It's a quack. That's what it's actually, that's the abstract data type. It's also a stack, because it could be simulating a stack, or a queue, if it's simulating a queue. All four things are the same thing in a way, just different views of the same thing. So whatever this thing is, we'll call it for the moment a quack, a linked list quack. The first element is called head. The data in that first element is completely irrelevant and is never used, and if you see it back again anywhere, anytime, anyhow, you have corrupted your linked list. You've done something very nasty, and you've got to abandon ship and say, oh my goodness, I'm going to exit this, this is not good. So if you ever see that data, your program has failed miserably somehow, because that is data that is not meant for consumption. It is purely internal data. It is a placeholder basically for the data. which is going to be occupied by all of the other nodes. So you see here that head data equals head data, which I've defined with a hash define up there somewhere, called int max, the largest possible integer. Could have made it 0, but 0 is just a little bit too easy. And if I ever see 0 again, I probably wouldn't think twice and think, oh, that's 0, that's easy. But if I see the maximum integer value, that usually, oh, that's a bit odd, what's that number doing there? And then you know something's wrong. So it's only an indicator that there's something wrong. So I'm using that location, that is an error condition. And it also has initially head next to be null. So in a sense now what I've done, I've defined a single node, exactly the same node as the linked list structure will have, but it's the null node. It's the empty node, whatever you want to call it, the starting node. From this point, I define the real linked list. Now, when I want to push onto this linked list, or do I do kush? I hope I don't do kush. I don't think I do kush, do I? No, I do. Go straight onto pop. When I want to push, I have data, data, D-A-T-A. Now, before I go and talk about the data, I have QS there, the second parameter. That QS is the name of my linked list. Q stands for quack. It is the structure that I'm pushing onto. It is the thing that is returned by the create instruction. You can't necessarily see that, but when you see the create, it has line 12. You see the left-hand side has type quack. You create a quack, it returns an empty data structure to you, ready to be pushed, not popped because it will be empty. So you can start pushing onto it, and you can pop and push or kush, whatever you like. So you get an empty data structure, but the point is it's defined. It has a name. The name that is returned by the create is the name that you give to push. And what push is doing is, oh, I've got a quack here. I'm going to add to my quack. How do I add to my quack? I've got to create a new node in line 30. That's malloc. Make sure I can do it. If I can do it, then my new node's data and next have got to be set. Okay, now, it's a push operation, which means it goes to the top of a stack. A linked list, the top of the stack is the first node, the head, if you like, of the stack, top of the stack. I shouldn't say you use the word head because that was the other node. The top of stack is where the push operates, the push is going to the other end. So the top of stack is where I've got to insert an element. Now in an array, when we're doing it with an array, it was easy because we just had an offset and we just said the array, whatever the offset is, equals the data, and you increase the offset, ready for the next thing. So it was just an array offset index that you keep up to date, and you know where you are in the array when you push and pop. That was easy. Now, all we know about the op data structure, what we've got, is we've got a head. Sorry, we've got a top. We've got a head and the next element, which is the top of the data structure, be it a push or be it a stack or be it a queue. So if it's a stack, then we're pushing onto it and we do the top of stack, which is the first element. If it's a push, we've got to walk through the whole lot, go to the very end, and then put the element on it. So there's a difference between the push and the kush, as before. So in this case, we're pushing, so we have to update that element. Now that element new node is going to be the head next. I spent some time telling you that in line 24, that right argument there, QS, is the name that's returned by the create. And remember, the create created a data structure which has as head node int max as data with a null. If we push an element now to our data structure, to our stack or quack, we then have to say, well, head, you had null as your link. Now you've got to update that, and it now takes new node next. Okay, so whatever it was pointing to before, whatever it was pointing to, if it was null, there's nothing there, and therefore your new next will be null. If it was pointing to this really long sequence, well, you want to know the head of that, sorry, not the head, I shouldn't use that word, the top of that, the first one, and you want to insert this new node that you've just done, new node, in there, which means you have to take that next node from QS and put it in to your link. And the Q next becomes you. You've suddenly become top boy. Top boy on the quack. Top boy on the linked list. Where top boy is not the first boy. It is the one that comes after head. It's actually the second boy or girl. I'll show you in the picture in a moment. So that takes some getting used to what's going on there. Popping is the opposite. When you pop, assuming that the stack's not empty, that you can pop something, you Q next, QS next. QS, remember, is the name of the quack that you're working with, the name of the linked list. The head node has int max as data and has a link to the first node in the data structure, which is the top. When you pop, you always pop from the top. Easy to remember. Whether it be a queue, whether it be a stack, you pop from the top. That means the first node, which is pointed to by QS, is the node that has to be removed. So you find from Q next who top node is. You quickly take the value because you want that value. That value is its value. So top node's data. You've got now who top node is. First node after QS next, or the first node after QS, which is pointed to by next. Then you have top node's data. So you've got the first data, the data on the first node, and the new next now, because you're taking an element out, I'm removing myself off the top of the disk, off the top of the quack, top of the linked list. To take myself out, who's my right neighbour? I've got to give that to my head person, my head node, because he knows who the top is. I'm no longer top, I'm removing myself from the list. So the QS next takes the top node next. My right goes to my left. The repeat of that left-right neighbour traversal or swap. And now I've removed myself. QS, the head knows of my neighbour, that's the new top. My data has been liberated, it's been given back in retval, returned on line 59, and I can now free myself. Free top node. I'm redundant. Okay, so this push and pop operations, the funny thing is this initial node which is the first, and the problem with these linked lists, with this data structure, the ADT, is you have to remember where the first is, the head or the top is. The head is a node which signifies where the first node is in the linked list, and the linked list is theoretically everything after the head node. The head node is just there to tell you where the first node is, and you must keep that head node up to date of who the top node is on the data structure. Now, empty stack is exactly the same as before. When you empty the stack, you just go through popping QS. Again, the QS is the argument that's returned by the create quack, it is passed to make empty, and it just pops QS until there's nothing left, until it's empty. So there's no change whether it's an array or whether it's a linked list, which is very comforting. That's make empty. If is it empty, you just check whether next points to null. Again, the head comes in, that head node, which has one link, to null if there's no linked list, and to the head, or sorry, the top of stack or quack, if it is a linked list there. So it just compares, it says compare the next with null. If they're the same, then I'm finished. It is empty. Sorry, it's true, it's empty. And to show the quack is the same thing as before, except for, of course, the loop. And here I've got a while loop. I set my top of stack, top of quack, in line 99. The first node in the linked list, I never print the head. It's got this ridiculous number in there, int max. It's got a pointer to the start of the data structure, and that's where I need to start. So the first thing I do is say, well, okay, let's get past the head and get to the top of the data structure. QS equals QS next. Now, while I haven't reached null, I print it. Print the data. And then I loop around, QS equals QS null. Next. Simple little traversal. It's almost the same as that, the free traversal we did before. I could have done that with a for loop too. Maybe I should have. There's no reason not to have done that. In fact, I probably will change that sometime to make it look like the for loop printfs that I had in Woolloomooloo. You can use a while or a for that thing, but with the free, you of course had to be more careful. Okay, note that create quack, that was just to refresh your memory going right up, that was the first thing we had, create quack, created something called head with data int max, and next being null, the empty list. That's what it created. So what's happening here? Create quack, a special head node of the linked list. The node is permanent and contains dummy data int max. It cannot be deleted. If the quack is empty, the head node's next field is null. If the quack is not empty, the head node's next field points to the top node of the data structure, of the linked list, of the quack. It returns the head, and create quack will return the head node to the client. Creates it and returns it to the client. The client then uses it for whatever he wants to do, to pop and push as he wishes. Although the client, of course, doesn't know of what a head node is, has no concept. All he knows is he's got this abstract data structure, if you like, and it's implemented through something, but it's sort of a thing which the system is happy to call a linked list. And not a linked list, is happy to call, what do we call that thing again? A struct node. I didn't call it anything. Doesn't know what it is, how it's implemented. That head is purely a theme as a result from the ADT. And all that the client knows is that it's got a type that's defined by a pointer. Okay, now I'm the nerd about doing it this way. So if the client is, for example, create quack, give it to QS, assign it to QS, then every quack command uses that QS, uses the head to carry out the operations that it has to. So if you push 1, 2, 3 onto the quack, you're actually inserting in the node after the head node a node with the data field 1, 2, 3. And you can retrieve information by popping QS, you can make QS empty, and you can show QS. So QS is the data structure which signifies, is the variable name, which signifies that you're working with a quack. Let's create, and now in this picture, I'll show you 3 pushes of data onto a quack. Pushes mean it goes to the top. So you see in the green, the second green, the create quack on the top gives me the head node. That's nothing, basically. There's no linked list yet. I do a push, and you see the brown push, it creates a data field. That's the actual node itself, but the next field in the original create, the head, has got to be updated. It's got to point to, it moves its data, what it was pointing to before, to your next data, the new node's next data. Whatever it was pointing to before, you don't know it's empty. All you know is you're pushing something onto it. It was pointing to null, but that's fine. It could be pointing to a number as well, or another field, or another node. So the new node has got to copy that head's pointer. That's extremely important. So that dotted line there, top dotted line, is a very important copy. The new node data is data, the new node next is QS next, that's that dotted line, and step 3 is QS next equals node. Update the head to point to you, the new node. Now, all 3 operations, 1, 2, 3, on the brown, happen again. Believe it or not, that's pink. My goodness. So believe it or not, 1, 2, 3 happen again with yet a new push. So this next push, the second push, puts a new data node in. And the other data, the one on the right there, is the brown one. This one's pink, believe it or not. And how do you do that? Well, the first thing you do is that you give yourself the data. You put the data into the new node. I create the data. I put it into the new node. Then I have to update the next field in QS. So that second dotted line, the one in the middle if you like, that gets put into my next, because that's my new next neighbour, right neighbour. And my left neighbour now, because I'm now the top of stack, top of quack, my left neighbour now is the head. The head talks to me. I'm the head, the top of the quack. And we do a third operation, just to bore you completely, possibly. We do it yet again. I'm putting yet another purple, this colour, believe it or not. I have to change the colours. They look too similar. So that third data is coming in. Everything's going at top of stack. Top, 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 top. It's a quack as a stack. It's putting it at the start. That's the top. In an array, you'd be going at the top, and the array would just be getting higher and higher. Here, we're putting it at the position right after the head, the top of the quack. And in a sense, everything is just shoving to the right. Well, shoving to the right means I'm inserting a new node. When I insert a new node, I give myself data, which is the data that comes into the push operation. You always push data, so whatever parameter I've got, that's my data. I have to then, my right neighbour is whoever the original top was, that's given by QS next, and I'm now the right neighbour of the old head, of the head. So 2 and 3 have happened. They're all exactly the same. Just going through 3 iterations of doing 3 pushes, or 3 iterations of pushes. So, the top of quack is always the second node. The push always inserts a new second node. The pop, always removes a second node. And the show quack never shows the head node. Now, you've got to get your head around that. Well, all this second business and head business and top business, and you've got quacks going on and stacks and queues going on and linked lists going on. I'm moving from abstract to concrete So concrete is the linked list, very concrete, but the abstract data structures is a stack or a queue, which I'm actually saying is called the quack, which is even more abstract. A quack can be a stack or a quack can be a queue, so that's a high level of abstraction. Then I've got the abstraction of quack or queue. Then I've got the very least abstract concrete data structure, which is the linked list. And they all have to cohabit, they all have to exist in a disciplined, systematic way. So the way this is implementation, and it's as good an implementation as I've seen, because what will happen if you don't have something like a head, you have to be extremely careful when you have an ADT of how you know where to start. If you corrupt that in any way, or have any doubts about the validity or verifiability of that, then you're in strife, because you could absolutely, completely destroy your whole program. One other way of solving this problem, more simply, but extremely dirtily, is just use a global variable, of course. And then you could actually cheat by saying, oh, stuff is ADT stuff, and passing of QSs and the head, and changing the neighbour of the head to a new top, and taking it out, and I'm changing neighbours, and oh my goodness, I just set up a global variable which remembers the head, and when the head changes, I just change the global variable, and I've just got a name called first something, first L, and I'll keep that up to date and keep it global. But that's dirty. And that means, of course, you completely destroy the ADT structure, and you can hack it. Anybody can hack it. That's got client privilege even. There's no separation anymore. Here's a pop operation in action. It's no easier, really. So if we have a sequence here where I've got the same 3 pieces of data that have just been pushed, when I pop from the same place that I push, which is the top. So I have to remove the second element. The second element, okay, there's my data, the purple one, probably see its data. The first thing is I have to say, who am I, where am I, what am I? If I'm popping, I just say pop, and I don't say anything more, just pop. They don't tell an argument or anything. So, okay, where do I pop? Well, I have to have the QS, of course. So where am I, who am I? QS next. The head's next is the top. So the first thing I do is I say, I am QS next. That's top node. I return, second step, I return my data. Because when I pop, I want the data. That's why I'm popping off the data. I can't throw it away. So I first have to save the data, which I call retval, in the function, which is further up. I then, in the third line, QS next is top node next. So here I got, for the third or fourth time, QS is my left neighbour, I'm top, and I've got a right neighbour, which is the second element in the linked list. I have to give my right neighbour's address to my left neighbour, that is the head. And I'm deleting myself, moving out of the picture. So top node next is being given to QS next as the new top node. And the fourth and final step is I free myself, I'm free. I'm no longer in the linked list, I'm a free agent. Nice way of looking at it. Okay, so this is in a sense the opposite of the push operation. Working in exactly the same place, but instead of adding something into it, or inserting something into an existing sequence or linked list, an existing list, I'm actually taking one out. So in a sense I have to do it the opposite way around. Now, here's a client. We saw this client before. Before I go any further on the client, you see 1, 2, 3, 4 with the pop. Okay, 1, 2, 3, 4. Remember that, 4 things, and 1 is top node, 2 is retval, 3 is fix up the head with the top node, and 4 is free. Okay, okay. Where did all that come from? Here. Line 53, top node is 54, retval is 55. Next is my top node, 56, free me. They're just those 4 lines. So I haven't made them up, I haven't been pulled out of the air. They are the implementation on the concrete data structure of that abstract operation Bob. Okay, that everybody is really clear that this code, what it means in terms of a picture. You really, believe it or not, even if you understand this, it's only an illusion, except for the highly capable, of course, and highly skilled. You think you understand and you sort of follow it, but when you have to do it, it is so easy to make a mistake and to forget what you've got, whether it's a pointer, whether it's data, and what you have to copy to what, and who knows who's linked to whom. It really is very tricky. And unfortunately, I have this dilemma whenever I give this linked list stuff. In an exam situation, what do I do? If there's one kind of question where students come unstuck with, it's linked list questions. Because if I ask you even to do something simple, it's so easy in the panic of the situation with anxiety that you just get a star wrong. You forget the star to the data structure, or you get a pointer wrong, and you could spend days trying to debug it in a normal situation, let alone in an exam situation where you may have 20 minutes to do that question. It really is very difficult. Linked list questions are cruel, I find, and it's always the worst performing question because they're just so easy to get wrong. And in a sense, I don't like them because I don't think they're a good test of your ability. It's too easy to get 0, even if you're a very competent programmer, just by making a small mistake. It tends to be either you get it right or you get 0. So all or nothing. Unfortunately, 10% get it right, the other 90% get very low. That tends to be the way it goes with linked lists. So I think, my goodness, how am I going to test the linked list stuff? What do? Arrays are much simpler. Arrays you all understand and feel in your bones, and you sort of know where the index is, and it's usually a fixed height. I've unsettled you all in a sense with the assignment because you've got to throw them away, and you've got to work with nullets, and you've got this: how big is everything? And so that is a shock in a sense to the system. This linked list stuff is even harder to get your head around, and it does require huge care. That's the other thing. The vast majority of you will not be careful enough, and through stress, of course, that exaggerates the situation. But real care is needed. You need to know what you're doing. You can't be guessing. Okay, so that's... let's go and have a look, maybe to make it a little bit more sensible to the client, because the client knows nothing. And that's maybe not a bad place to be. So in the client, exactly the same as before. This is the client, remember, that reversed the command line arguments. Now, we're only the first lecture in week 4, but you should be looking at that program and saying, oh, goodness gracious, did I ever not understand that? That is so simple. That's trivial now. This is after 3 weeks of the course. Well, I sort of hope you like that, but maybe you look at that and say, I've never seen that in my life. What is that? What language is that? Goodness knows. So I'm now setting my char pointer input to my argv1. Char pointer is a pointer, it's an address. argv1 is an address. It's an address because argv is a 2-dimensional structure. And when you take a row of that structure, you're left with a 1-dimensional structure, which is what input C is, a 1-dimensional data structure. Okay, that's the way I look at it, that argv, actually you could have argv1, 0, which is the first character of argv, first character in the string argv1. argv11 is the second character. So if you're only interested in the whole string argv1, a whole string argv1 or 0 or 2 or 3, you just take that index 1 or 2 or 0, 1 or 2 or 3, whatever. You can assign that to a char star because they're the same type. And I now take those characters. I create my quack. I call it S instead of QS. Okay, it's a stack, so I'm calling it S, not a QS. As long as I don't have my terminator, my null terminator, I push my character onto the stack. That stack is a linked list. You can't see that. Thank goodness. You don't have to maintain that. Even greater, thank goodness. It's all done for you behind the scenes. That's the advantage of an ADT. That's why you do not want to use global variables. Not only don't you want yourself or anybody else to hack them, you don't want to maintain that. You don't want the responsibility. You want let the ADT sort it out. It's ADT's problem. All I want is to push a character from argv1 onto the stack. And then I increment the pointer to the next character. So I'll do argv1 0, argv1 1, argv1 2, argv1 3, etc. until it gets to the null. It puts them all on the stack. Then I empty it. Because when I put the first character, second character, third character, fourth character, etc., the last character I put on is the top of stack. When I start popping them, I get them off in reverse order. So as long as I haven't got the empty stack, I'll pop the blighters and put them and just do a print on them. %C. And in the end, when I'm completely finished, I put a new line out, put char. And I don't even show you it working. Did I forget to do that too? I really had it. Oh no, I did do it. We now have two implementations of the quack ADT. We have the array version quack.c. We have the linked list version quack.ll.c. Both use the same interface quack.h, of course. Compile and run both with the same client revarg.c. So DCC quack.c revarg or DCC quack.ll.c revarg. No difference. Both of them compile perfectly, and I can run it with a string 0 to 9 and both reverse the string. When it's just so nice, when you see the final polished result, it's almost nothing's happening. It looks so simple. But behind the scenes, you as programmers have to realise that there's some real careful, what would you call it, pointer manipulation going on to keep this linked list intact. To have a head pointing to a top and in sequence or as a list with pointers all the way to the bottom, which is null terminated, the last element, the last node. Last week I asked you, and we went through very quickly, to write push for an array, quack.c, push, I was provided, I didn't give you push, went through very quickly. You can, of course, I haven't given you push for a linked list version. And you think, oh, what's going to be involved with the push? With the push, I go at the top, which is the neighbour of the head, which is QS next. But with a push, I've got to go to the very end. Well, that doesn't sound too bad, because I don't insert at the end, I don't insert at the head and muck around with the next on the QS and put myself in and the neighbour left to right. All I do is go to the very end until I get to the null, and then I have to say, well, that null is wrong, null is me, and I'm inserted. So if I make or create malloc room for myself, I give myself, or I assign myself to the null address pointer in the last element. And I've pushed. So push is actually quite trivial. You think you should have no trouble with push at all. With a linked list, it's really easy. And then you can run Flavius's circular buffer using a linked list implementation. And it's no more exciting than that. You just give it 10 and 3 or 12 and 5 or whatever numbers you want, being the size of the linked list, or the length of the linked list, which person you want eliminated at every step, and it works perfectly. That's it. That's all I want to do today. I'm finishing a little bit earlier than normal, but I think that's enough. The linked list stuff may traumatise a few of you. You've got your hands full to get this assignment done. I must admit I'm just a little bit worried about some of you that are still battling with the basics of it. All I can say is if you have any trouble, forget. The first restriction you forget about is the array, getting rid of the arrays. Leave the arrays in. Okay, leave the arrays in. And second thing is, try to maximise the number of bad cases you can pick up. That's worth marks. The arrays is, if you like, the difference between, I don't want to actually commit myself, could be the difference between a pass and a distinction, the kind of thing. It really move you up if you have a good implementation with no restrictions, no arrays. Okay, so know where your priorities lie, get it done first with an array, have that version ready, and then you can play with the non-array version. If you don't get it working, if you've done a good implementation with arrays, which does a lot of checking, and you can't find a bad array which is not picked up, then you'll pass. No problem. Okay, I guarantee you'll pass with a good implementation with arrays. That'll only be a pass. That's a basic rough guide to the marking. Okay, the non-arrays is for the ones that want better marks. Okay, thank you. See you on Thursday.
The value of having a head is that it never changes. So the QS always has a starting point. The moment you take that away, that head, and you say, I've only got a top, the top operation takes away the top. That means you have to change the head.
I was providing QS to be now. Like,
How do you do the top? What's the top? When you do a second pop, what's the top? Every time when you do a pop, how do you know what the top is? Maybe I should give an exercise where
I was expecting to do some kind of check that this is equal to max set. But like only one place I saw that check and check that the value is equal to max set.
I did that for corruption in justice act, yes.
Only there.
Yes, because it's never necessary in a sense.
So in that we could actually do away with it.
Yes, and I see where you're coming from now. I'm only showing you a minimum set of functionality. There are a lot of other things you can write where you can traverse from top to bottom in weird ways. You can insert and remove things in weird ways. You can do all sorts of things. And really doubly link them as well. So there are all sorts of things you can do. And in the cases of when you're doing really weird things, you do want to have a check on that first mark there. Now, in this case here, the only time when I popped it, could I do it? I'm not sure whether if it was possible to do a check on the head node when I popped it. When you push, when there's a head there, I suppose I could have had it in front of every one to make sure that the QS that I've got is the head. I suppose I could do that. It would have added.
These functionalities, I think, without that maxed in.
I can change it. There's a lot of extra code which will be the same for everyone. Maybe it's a good idea. Maybe I could have had every function. I could have had a check, a call, check head. That's the call to check head, which will take QS, and the only thing check head would say would be true if the head's there, and not true if it's not there. And then I would have every function. If check head or head okay, then boom, 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 and the whole function will be there. Maybe that's not actually a bad idea. Maybe that would give it a lot more strength. But the more interesting question, I thought, what you were asking me was, why do you want the head? Really, in the sense,
Not the head exactly, but not using that head value. Like
I see. Okay.
not
Yes, you're right. Maybe I should
have a pointer to head, but start using the head itself. Like store the first value in the first block.
Oh, no, you can't do that. No, because then you've got no head. It's now the top. If you make the head the top, you've got a top. It's hard to keep it up to date. When you do a pop, what do you do? Explain to me a pop.
Like if there is a value, if it is null, let it be null. Otherwise,
What's null? We're talking about, when you're talking about it's a next is null.
we have one QS. So we have two cases. One is this, just one value, or where there is nothing. So first check if QS is null, then null. In case of a pop, there is nothing to do.
I thought you were putting a value instead of internet. You're putting a value in there.
Yeah.
So what do you do when you pop? Do you get rid of it completely and have it null? So there's no QS anymore.
Your QS is null.
But then what's the difference between QS being null and not having defined the QS?
No difference.
But don't you have a problem with it? Now we're talking about never being created.
Yeah, according to what I said, the create would actually return null.
Yes.
Create would return null.
And that's fine. Okay, that's just the start. That means that you're not differentiating between we've never initialized it because it's null. I mean, if I just have QS equals null in my main program, I don't call create at all.
Yeah, I mean, create function itself returns null.
But if you don't do that, QS can still be null. My point is that you can have a non-existent data structure when you're trying to push to, or you can have a zero data structure or an empty data structure which you're trying to push to. If it's an empty data structure, it's fine. But if it's just zero, it's never been defined at all. It's QS equals, yeah, what you've got in your program is quack Q equals null. That's fine. And then you could do push.
Yeah, we could do it.
But it's never been, what are you going to push to? There's no data structure.
So push would actually create a simple node, and if Q is null, Q would be new.
So it's going to return.
Q would be new.
Okay.
If Q null,
And that's what's returned. Now, how does that value, then you've got to be careful, you remember that value, so when you do another push, another pop, you each have to keep that up to date. That QS, it's changing all the time. Every operation changes that QS.
there is one. You just have, for a pop, you just have to do QS equal to QS next. Check if QS is null. Otherwise, do QS equal to QS next. And yeah, of course, delete and free that space up.
Yes, but you will have a varying front. You haven't got a single point. A bit like Woolloomooloo, where you don't remember the first. You don't have a fixed point to start the data structure. Let's finish this now. What I will try and do is I'll think of an exercise which will bring out what happens when you don't have a head. I think it's what happens when you have a headless linked list. That's a basic question.
Like, I mean, this is actually head. It is not headless in the sense I could just still point, tell the head is Q, where Q head is
Your
null.
head is your top of stack.
Yeah.
And if you don't have a top of stack, then you have a null head. And the head is null, and that is your head. So it's a bit like the tail is points to null, the last element is a null pointer. You're saying your head is null. So